today's quiz?
I will share the answer key in Teams itself. Sure.
Yes.
Okay. We'll start our today's session. Last class we had been discussing about product ciphers, right? And how the components are being made and a structure of product cipher we came across this one, right? Now we move on to classification of product ciphers. So if we take modern day block ciphers, okay, we can able to classify them under two categories called Fiesta cipher and non-Fiesta cipher. So what does this term means in sense? Fiesta ciphers are nothing but a block ciphers, but they will have the components of both invertible and non-invertible property. There is the components which have been used, like we just saw 6 components, right? Starting from P boxes, S bots, XOR operation, circular shifting, swapping, split and combine. So these components, they have both invertible property as well as non-invertible property. So if we take a PSL cipher, it includes all block ciphers which are going to have all the components, both invertible as well as non-invertible. Then we have a set of block ciphers which comes under non-Fiesta cipher. That is, these components will have one and only invertible components present in them. So compared to Fiesta cipher, non-Fiesta ciphers are very easy to design. Right. Now we move on towards this discussion over Fiesta ciphers. Okay, Fiesta ciphers have been there in the existence for past more than 2 decades. Okay, so these Fiesta ciphers will have three categories of components. Okay, you should actually speaking, you should put this in terms of types. You should use this as categories. Okay. Okay, categories of components. First one is self-invertible, like how we have our straight P boxes and XOR operation. Okay, these things are self-invertible, and invertible components like your S bots. Okay, those things come under invertible component. Then non-invertible component like your expansion P bots, compression P bots, those components. So these three categories of components will be there in Fiesta cipher. To start off with, we'll start with the very basic structure of a Fiesta cipher. Okay, so in this we have a mixer. Okay, in this mixer, it is a combining technique where you're going to combine a non-invertible function, that is this function f. Okay, f letter is a mathematical way. It's some algorithm, okay, which is going to operate over the key. That is, if you are supplying a key to this function f, it is going to perform some mathematical operation over this key. Okay, and the output is going to be XOR, okay, with the incoming input. Okay, that is the main objective of this mixer, that is the yellow box. Okay, as I said, XOR will cancel the non-invertible function during the decryption process. Okay, we will see how it is going to do. It's showing that f is a non-invertible function. Being a XOR is going to be appended along with this non-invertible function. It is going to remove that non-invertible property. Okay, assume that this is a scenario, right? We have a plain text P1, which is a block cipher, okay, which is given as an input to the mixer, and mixer is going to be performing the XOR operation with a function. This is like your encryption algorithm, okay, and this encryption algorithm is going to get an input from your key called K. So I'm using f of K. The output of f of K is going to be XORed with P1 to give me the C1, that is a ciphertext. Right. So assuming that it is a lossless transmission from the transmitter to receiver. So whatever C1 is transmitted, it is received at the receiver as C2. Okay. So under the condition that C1 is equal to C2, now how we are going to recover this plain text P2? So P2, once it is recovered, it should be same as P1. Then only we are properly transmitted, properly encrypted and properly decrypted. If you see here, the encryption part C1, they are computing C1 as P1 XOR with f of k. This is what we just saw here. Sorry guys. Then next we have the P2, that is the decryption part, and our main objective is to retrieve the plain text. So the plain text P2 is obtained from XORing the received ciphertext with f of k. Being a symmetric key cipher, they are using the same function at both encryption and decryption and the same key for both encryption and decryption here. So as I said, C1 and C2 are same. I replace this C2 with respect to C1, and we already know that C1 is nothing but P1 XOR with f of k. So if I replace this one with this P1 f of k, I'm getting the expression like this. And if you are going to XOR the same component, like 1 XOR 1, I'm going to get 0, 0 XOR 0, I'm going to get 0. Right. So this f of k and f of k will run for 0. It should be leaving me the plain text back. So that now your P2 is equal to P1. That is whatever is transmitted as a plain text after encryption is decrypted as P2. Right. Is it clear, guys, the basic structure of Fiesta cipher? If it is clear, raise a hand, because if you have any doubt in this part, kindly ask me. Then only you can able to understand the enhanced version of Fiesta cipher. Okay, I hope it is. Thank you, Gashish. It is clear. Right. Move on to an example, like how one example of how this function will look like. So in this example, they're saying that the plain text and ciphertext are made up of 4-bit, okay, and key is 3-bit long. Okay, and the function which is going to operate over this key, what is going to do the sense, it's going to take the first and the third bit of the key and going to convert them into decimal number. After converting, it's going to square the decimal number. After squaring, it is going to convert it again into 4-bit binary number so that it can able to XOR the output with the plain text. You'll see an example here. Assume that this is the plain text you have 01111 and the key is 101. Okay. As per the rules of the function, it is going to take first and third bit of the key, that is 1 and 1 is going to be taken. Okay, you can able to see 1 and 1, and it is converted into a decimal value as 3 here. Okay. Then they are squaring the 3, which we get 9, and if you convert them into binary, we get 101. So for encryption, they will do the plain text is 01111. The output of f of k is 1001. They got the ciphertext, and the receiver, this is the ciphertext received, and they are recreating this f of k, and if XOR, they're getting back the plain text back. Right. Now we move on towards the improvement of Fiesta design. So some modification they made. Okay, that is they made the mixer to do more complex operation. Okay, and they want to involve the plain text also inside this function. Okay, the input for the function f, okay, is going to come from one half of the plain text and the key, and at the receiver end also it's going to get 2 input, right? So how it's going to work? And here they are saying that they're using the same value of k here, and they say that the function f must have the same input in both encryption as well as in the decryption. Then only the f of the function f will produce the same output here. And if you say here you have the left half and right half, that is the given block is equally divided into 2 halves, and left half is taken here, and to get the function's output, I'm giving the input of right half of my plain text and the key, which is going to give me an output, and if it is XOR, I'm getting the ciphertext C1 left hand side. But here you can able to see the right hand side of my plain text P1 is exactly transferred to the right hand side of my C2. That is, the R1 of P1 will be equal to R2 of your C1. Both are same, right hand side. And the decryption end, again, it's a reverse process, that is left hand side is taken, and here they're taking this right hand side part of my received ciphertext and the key to get the output here. So if you want to see this description very clearly, okay, and if here also assuming that there's a lossless transmission, your C2 is equal to C1, which means that your L2 will be equal to L3 and R2 will be equal to R3. This is the first assumption we are taking. Okay. And if you look carefully at this signal flow in this model, all the right hand side, that is your R1s, R2, R3 and your R4 all are same. No manipulation is done or no encryption is done on the right half of the plain text. So R4 will be equal to R3 is equal to R. So our ultimate aim is nothing but we have to prove that this L4 is equal to L1. Whatever the plain text transmitted, I am going to retrieve this as a plain text at the receiver end. So L4 can be written as L3 XOR with F of R3K, right? L3 XOR with F of R3K, and we know that L3 is equal to L2. At the same time, R3 is equal to R2, right? And if you check how this L2 is computed, if you check L2 is computed as L1 XOR with F of R1K. This is your L2. Now this part, this R2 is again changed to R1. We already saw that R4, R3, R2, R1 are same. So at this point you can able to see both the functions are same. I'm going to get my L1 back here. Is it clear, guys? If it is clear, raise your hand. If you have any doubts in this part, you can ask. Very simple to understand. Right. Now in this model also they had an issue, that is the right half of my plain text is going without encryption. So any attacker at least he will come to know one half of the message. So in order to improve it further, okay, the final design of VSL Cipher. Okay, here they went with multiple rounds. Okay, the thing they just simply made it sense they added this swapper. That's all. You can able to see up to this part is your previous design. They have the left hand side, right hand side of your plain text. They're going to XOR with F of R1 K1. Once they get the output, here they are swapping. That is, the encrypted one is going and sitting in the right half. The unencrypted one from the round one is sitting here. So in the next round, this part is going to be encrypted here again. So after 2 rounds, you can able to see the entire plain text would have been encrypted. Right. So here the one thing people have to remember here. One is here instead of using key called K, they are using K1 and K2. Okay, these are called as round keys. That is for each and every round they will be using a unique key and the same key will be used here. So if you see the signal flow in the encryption part is from this is your plain text, this is your cipher text. And here this is your cipher text and this is your plain text. So here the signal flow will be from bottom to top. So here this is round 1, this is round 2, whereas here this is round 1, this is round 2. And the key K2 which is used at last in the encryption will be used first here, and the first key used in the round when the encryption part will be used last. Sorry. Right. So if you sorry guys. So here L3, R3, L4, R4 are same. That's the only thing we have in our thing, right? And you have to prove that L6 is equal to L1 and R6 is equal to R1. You have to prove this one, right? So I just go through this one. Okay, I just shared the slide. It's the same principle which you just saw in the previous model, right? Now, if you move on to non-Fiesta cipher, I mean, as I said, non-Fiesta ciphers are very easy to design. It's not all immutable components, right? So I hope you people are now clear with Fiesta and non-Fiesta ciphers, right? If it is clear, raise your hands. Because if you are not clear with those parts, you can't able to understand the most important topic which we are going to discuss now. Thank you, Arun. Thank you, Kashish. Okay. Now we move on to the next, the most important topic in this module. One of the famous modern day block cipher called data encryption standard, shortly called as DES. Okay. So if you see the history of DES, it is coming under symmetric key block cipher, and it was published by National Institute of Standards and Technology, that is NIST. And when this started in the sense, NIST people want to create a well sophisticated block cipher, okay, and a symmetric key crypto system. So they called for many proposals in the year 1973. Okay, out of many proposals, the proposal submitted by IBM, okay, under their project name called Lucifer, okay, this DES was born. Okay, so this DES was accepted from the IBM's people and which was published in the public for public usage in the year March 1975 by FIPS, that is Federal Information Processing Standard Organization. Right. So from 1975 onwards, DES came into existence. Later in the early 90s, it has been modified into next version. But still, we people are using this DES algorithm. Right. So to see about the overview of DES, the DES block cipher, this point you people have to be 3 points you people have to keep in mind very clearly about DES algorithm. So if you take a DES algorithm, the block size, the number of bits each block can hold in plain text is 64-bit, as well as the cipher text will also be 64-bit. To convert the 64-bit plain text into a 64-bit cipher text, I'll be using a 56-bit key, cipher key or encryption key, whatever you call cipher key, because it's going to be used in both encryption and decryption. Okay, so as of now, you people should know what is the size of a block in a plain text in DES algorithm, what is the size of a block in ciphertext in DES, as well as the size of a cipher key. So 64-bit plain text, 64-bit ciphertext, and 56-bit cipher key is used in DES algorithm. Right. So if you see the encryption process, how this DES algorithm is going to work, you see it has totally two permutations, that is two p boxes will be used. Sorry guys, and these boxes are called as initial permutation bots and final permutation bots. Along with this, it will have a 16 Fiesta rounds. So if you see the previous thing, we just saw a sample of only 2 rounds here, right? Like this, we'll be going to have 16 rounds. Okay. So in this, we'll be discussing how this initial permutation, final permutation works. Then we move inside the round. Then inside the round, we'll move into the function, how the function is designed. Then we see few examples. So this is a general structure of a DES algorithm, how it will look like. So here comes the input, that is a 64-bit plain text will be coming as input, which will undergo initial permutation, which will be a p-bots. To be specifically speaking, it's a straight p-bots. The straight p-bots. Then comes your Fiesta rounds from 1 to 16. And here you people should be very careful here. Whatever we just said is a 56-bit key is used for, it's called a cipher key used for encryption, will be given as an input to a round key generator. And this round key generator will create different round keys, totally 16 round keys. And this round keys will be of 48-bit. So there's a difference between an encryption key, that is cipher key, and a round key. Okay, cipher key will be used to create the round keys. Each round key will be 48-bit length long, right? Which will be supplied for the each and every round to produce the output. And after 16th round, again I'll be going with the another p-bots, which is also straight p-bots, to get the final ciphertext output. And one thing, there is a relationship between this initial and final permutation bots. Both are invertible to each other. As I said, your straight p bots are invertible. Both are inverse to each other. Right. This is a general introduction about your DES algorithm. If anyone have any clarity issues or anything you need, means you can ask me now. If it is clear, raise your hand, guys. Okay. Okay then. Right. Now we move into initial and final permutation bots. So here initial and final permutation bots, as I said, it is a straight p bots. Here we are going to have 64 cross 64 bots. That is 64 input and 64 output. So if it is 64 cross 64 bots, can you tell how many are how many combinations of such bots can be found? And being a transposition cipher, what is the way? 2 power n factorial or n factorial? or log? I hope you get the point what I'm asking. Can anyone tell how many different combinations can I able to get if it is 64 cos 64 straight p bonds? 2 power n factorial. Kashish, actually, if it is substitution cipher, what you're saying is perfect. But being a transposition cipher, we'll be having only n factorial. So totally, we'll be having 64 factorial combinations. Okay, 64 factorial combinations we'll be having. And
so each will be having one connection, right?
Yes, actually speaking, totally different. I mean, this is one of the combination of 64 factorial. This IBM people, they used only one combination of them. It's a fixed one. It's not going to change for each and every iteration or anything. So whatever the plain text is going to give, your input pin 1 will be always connected to 40 here, and the 58th pin will be always connected to 1 here. Being in inverse bots, you can able to see if one is connected to 40, in the output the 40th pin will be connected to first one here. Not totally 64 factorial combination. This is one of the combination they used, and they don't have any justification for why they chose this particular bots, but they prefer this one. So if you see the initial and final permutation bots used in DS algorithm, this is how it will look like for all the 64 combinations, 64-bit combination. So as I said here, the value shows the input pin, and the position of this value, which is placed in the first position, gives me the output pin. Right. And this is totally inverse. Initial permutation bots is inverse of my final permutation bots. Both are inverse to each other. Right. I hope you people are clear with what is initial permutation bots. Is it clear, guys? If it is clear, raise your hand. Next, we'll see a sample numerical how this permutation is going to be done. If it is clear, raise your hand. If you have any doubts, you can ask. I hope.
So can you tell us the total number of combinations again? Because
okay, total number of combinations. I mean, generally, generally speaking, if you have a 64 cross 64, you'll be having 64 factorial different combination. That is, one can be mapped to 1, or one can be mapped to 2, one can be mapped to 8, one can be mapped to 9. So like this, there are many ways we can able to map this single input pin. So out of this, they used this one map to 40, 2 map to 8. This is these like this. We have 64 factorial combinations we can able to have. So out of this, they choose these two combinations alone. I mean, to be specifically speaking, they choose this one. So the other one will be inverse of each other.
this.
Yeah, okay. Right.
Also, sir, DES is based on transposition cipher.
We can't able to say exactly only transposition. DES has a combination of both transposition as well as your substitution. For example, if you see the DES structure, in this P boxes only your transposition is happening. But if you enter the Fiesta rounds, okay, here your substitution techniques will come into picture. So it is a combination of all these things, transposition, substitution, both.
So then, sir, how can we say that it's only n factorial, the number of combination, total number of
No.
combination?
Now I'm speaking from with respect to this initial permutation bots alone. I'm not speaking in the overall DES structure. I'm just speaking about this particular P bots alone.
Okay, sir.
Is it clear?
Yes, sir.
Yeah. We'll see in a sample numerical. Here they are asking you to find the output of a final permutation bots when the input is given in hexadecimal value. So here they given you a hexadecimal value. The first step you have to do is nothing but you have to convert them into a binary value. How many of you know how to convert a hexa into binary? Can you raise your hand? At least using calculators or any method. Okay, superb, Arun. So is it possible for you to tell me the binary version of this such a big, actually, if this is a hexadecimal value, totally you have 16 characters here. If you convert them into binary, each character will be a 4-bit, so totally you'll be getting 64-bit. Okay, I'm happy that at least Kashish and Arun both know. Okay, for people who don't know, I'm just saying simple way is nothing but take this first 0 represent with using 4 binary value. Again, go for this one. Like this, you'll be going for each and every character. Okay. So can you tell what is the value for 4-bit binary equivalent for this 8? Hello. You can use chat. You can use the chat bots. 8 alone. Yeah, thank you, Kashish. So for 8, you'll be getting 1. So here we have zeros, 1, 000. And again, the zeros will be following here. At last, this 2. For this 2, what will be the value you'll be getting? 4-bit equivalent binary value for this 2. Yeah, it is 0010. So if you expand everything, totally you'll be getting 64 bits. In this 64 bits, there are zeros, ones, 00 and 10. So what, according to the permutation bots, actually speaking, they're asking for final permutation bots. So you have to take the 40th pin there and you have to map it to first one, 08, that is 8th pin to second one, then 48 pin to third one, and go on and goes on. If you do like this, that's all. For the entire fat paper, you will be sitting for this one alone. But easy way here, what it is, because there's no use of shifting zeros, nothing going to change. The easy way is in the sense, take this 64-bit length, you have to find where are the ones are not sitting there. So if you check here, the ones will be sitting, okay, this one, okay, will be sitting in 25th position. For example, this is 4 plus 4, 8, 12, 16, 20, 24. So 24 zeros, then comes 100. So this one will be sitting in the 25th position. Okay. And at last, I will ending with 1 and 0. Last bit is 64th bit, the previous one will be 63. Right. So now all I have to do in the sense I have to shift only these 2 bits where 1 is present. So I will have to search in the final permutation bots where this 25 and 63 is sitting. So 25, if you see, it is sitting here. 25 is sitting in the 64th position. And 63, yeah, 63 is sitting here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15th position. Right. So now you have to create another 64-bit. Okay, starting from 0, 0, 0 and goes on. Place exactly 1 in the 15th position and you keep on writing zeros. Then you place another 1 in the 64th position. Okay, now if you convert them back into hexa, you will be getting the output of a permuted, and this final permuted output here. You will be getting the answer as 002 and goes on. Is it clear, guys? How to use this permutation bots?
Sir, can you please explain once again?
One second. So, at which point you lost me? Can you tell? Sorry.
The previous, like on the table, after locating the respective positions, then what do you do?
Okay, okay. So you understood how to convert base hexa into binary and how to find the ones in the binary, right? So exactly
Yes,
now
sir.
you found the ones in 25th position, 63 position after converting. Since they ask me final permutation bots output, I'll go to this final permutation bots here and I'll check where are this 63 and 25 is present because I have ones in 25 and 63 position. So once I found the 63 here in this table, and this position of the 63 is nothing but starting from this is 1, 2, 3, 4, 5, and goes on 6, 7, 8, 9. This is 9, 10, 11, 12, 13, 14, 15. So 63 is sitting in the 15th position, right? Like this, the other value of 1, which is the 25, is sitting in 64th position. So what will be the output in the sense, wherever I'm finding these values, no, there are no ones are there. Rest of the places I don't have any ones. So I'll be starting with 0, 0, 0, and I'll be keep on writing zeros up to 14 zeros. I'll be placing my 1 here, then I'll keep on writing the zeros, and here also zeros will be there until I reach the 64th bit where I'll place a 0. So if I convert this into back into hexa after writing this one, you'll be getting the output as the 002. For example, as I said, 1, 2, 3. Okay, so totally here 4 zeros, here 8 zeros. So up here 12 zeros. 2, if you represent this 2 in binary, what will be the answer? 0, 0, 1, 0. Right, so this 1 will be exactly sitting in the 15th position. Right, and at last, if you represent this 1 again in the last one, it will be getting 0, 0, 0, 1. It will be sitting in 64th position, 64 and 50. And no need to show which bit is shifting. For example, 25 is shifted to 64 because it is clearly visible if you are using these bots. So after identify, yes.
So while doing this question, do we have to convert it, like show the conversion to hexadecimal first and then to the binary?
Yes.
Sorry, binary then to hexadecimal, because that will take a lot of time.
No, actually speaking, conversion in the sense, no need to show all these zeros, but at least you have to show me where are the ones are sitting. I hope you get my point. Instead of writing 0001, show me this is the hexa, the binary value, these are the ones sitting, and these are the places ones are there. As I showed, as I said, only 24 and 64 third bit are ones, other bits are 0. So using the final permutation box, I have shifted these things, these positions, so I am getting the output like this. Is it clear?
Yes, sir.
Yes, sir. So, sir, that permutation box will be given, right?
Being an open book examination, so we are not supposed to give. You people should have the bots with you.
Okay.
Being a, if you have a book with you or if you have the material, obviously you're going to have this with you. Bots will be there, right?
Yes, sir.
Yeah. And be careful in examination whether it is asked for final permutation bots or like this one initial permutation bots, right? Because if you change the bots, your entire answer goes wrong. So this is nothing but the previous output which we got. If you convert back them, for example, the input has two ones. One is sitting in 15th position, 63rd position. If we go to our initial permutation bots, you can able to see. So that is where is 15 sitting. 15 is sitting here. 15 is sitting in 63rd position. And I have to find 64. 64 will be here. 25 means here. This is in 25th position. So you can able to see it's totally inverse. Where 15th position, 63. So in 63rd position, 15 is there. 25 is sitting in 64th position. So 64 is sitting in 25th position. Totally inverse. Is it clear, guys, regarding this initial and final permutation? If it is clear, raise your hand so that I will move on to next one. Okay, thank you, Kashish. What about Haru? So only 2. Fine. So as of now, some people would have got it out. So the initial and final permutation bots are straight P bots and the inverse of to each other. Then what is the use of using both? Because if I simply connect these two bots as like this, if you remove the 16 rounds, if you connect these two bots directly, whatever the input I'm going to give, the same output is going to be obtained here. Initial and final permutation bots doesn't have that much influence in the DES algorithm, and those people have not mentioned what is the significance till now. But since those are the people who have introduced a system, we are using that initial and final permutation bots. Right. Now, if you move on to the round structure, how this round structure of our DS algorithm looks, the same round structure which we just finalized in the VSL cipher. That is, you have be having a left half and right half. Since DS algorithm, you're using um, 16 rounds, right? Sorry, 16 rounds each giving input of 64-bit plain text. Okay, here I'll be having left half of 32 bits, and your right half will be another 32 bits. Right. So here again the mixer, which will take a function of my right half of my 32-bit and key, that is the particular round key. Okay, and swap, and this will be the output. right? And if you move on here, the main thing, that is what is happening inside this white box, this function. In this white box, which is called as heart of DS, okay, here this DS function is going to be supplied with input of only 32 bits because only the right half of my previous input, round or the plain test is going to be given. Then comes the expansion pbots. This expansion pbots is going to convert this 32-bit into 48-bit. Then only I can able to XOR with the input round key, which is a 48-bit, right? And these 48 bits are given to 8 SBOTs. So totally 8 SBOTs are there. If I divide this 48-bit with 8 SBOTs, I'll be getting 6 bits per bots as input. But this 8 SBOTs is going to give me a out, because this is getting a 48-bit, so we are getting 6 bits per bots. But it should produce only 32-bit as output. So to produce 32-bit as output, how many bits should be produced as output from the bots? Can anyone tell per bots? So 6 bits, 8 bots, so I can able to accommodate 48-bit. But output should be only 32-bit. So if I give 6-bit as input for single bots, how many number of bits should be given as an output from the particular bots? Can you tell? Yeah, Kashish, yeah. Right. So like this, it's a 6 cross 4 SBOTs, which will give me 32-bit. Again, I'm introducing straight pbots. So exactly speaking, here I'm introducing my confusion property and my diffusion property. As I said, this SBOTs is obviously a substitution cipher, and pbots are your transposition cipher. It's a combination of both, right? And going to produce again 32-bit, and it's taken as output, which will be again swapped, and we'll move on to the next round. So this is the general structure of a DS function. Okay, we will see in deep how these functions works on in the next class, right? So anyone have any doubt in today's topic, you can ask me.